the second part of ESR spectroscopy. I am myself Dr. S.P. Deshmukh, Department of Chemistry, DBA Dayanand College of Arts and Science, Solapur. So as we see in previous PPT, so we proceed further to understand how there would be interaction. So there are having majorly this ESR spectroscopy works with having interaction of its own dipole moment, electron dipole moment with applied magnetic field. So in first case, hyperfine interaction, and that we call as a electron nucleus coupling. So it would be understand with respect to E is equal to G, mu of B, B of 0 and M of S. So what it means? It means G is a proportionality constant, mu B is a Bohr magneton. It is MS, it tells us the electron spin and B0 magnetic spin, and then quantum number. So interaction of magnetic moment with unpaired electron with applied external field. So this hyperfine coupling is nothing but the magnetic interaction with the electron spin and nucleus spin. When both are having not equal to 0, I is not equal to 0. So it should be used to be major interaction. Then question arises, there is a having how multiplet we get it. So when we go for the fine structure for the ESR signals, there is having zero field splitting, or that we call as a Kramer degeneracy. So what it mean by Kramer degeneracy? Kramer degeneracy is, it is observed, it is having zero field splitting because electron having its own magnetic moment. And when its own magnetic moment or that we call as a dipole moment interact with in absence of magnetic field, but they have to interact with surrounding media or nucleus, leads to they have to split into two different levels, which leads to zero field splitting that we call as a Kramer degeneracy. But this degeneracy would be split when we apply to the again magnetic field. So there are having two cases. One is having even number of unpaired electron. So in case of even number of unpaired electron, even means 2, 4, 6 like to be. And their total spin counted to n plus 2, in which S is equal to 1. Then at that time they have to show M of S minus 1, 0, plus 1. So that way they have to get minus 1, 0, plus 1. That is a total spin, we get it 1 when there is having even number of unpaired electrons. And then second case where having odd number of unpaired electron, then at that time the spin used to be minus 1 half plus 1 half, minus 3 by 2 plus 3 by 2, and they have to show such type of splitting. And in zero field splitting, there is a Kramer degeneracy, while here when we have to apply magnetic field with having how many number of unpaired electron, even or odd, based on that they have to split into the this way. So this is the multiplet structure of ESR. And then next question is what it mean by hyperfine interaction. So hyperfine interaction is nothing but the spin of electron with the surrounding nuclei, and it can give the better information about the how there is a separation of two surrounding peaks or neighboring peak, and also they have to tell the distance between unpaired electron, and it also gives the idea about the how they have to interact with the nuclear, and that would we get it with respect to this equation, and that equation tells us hyperfine coupling constant and nuclear spin quantum number, and it majorly determines the distance between two successive signals. Therefore that hyperfine interaction, or what we call as a nucleus electron coupling, playing crucial role to understand how we get peak and why we get this type of peak. Then there is having selection rule. That selection rule tells us delta M of S is equal to plus or minus 1, and delta M of I which is equal to 0. With respect to sum of NMR, this principle would work. But here what we have to say, there is a having nuclear which can having its own dipole moment which interact with having electron with having its own spin. But when we determine how many lines we get it by a simple equation, that is a 2Ni plus 1. N is how many number of equivalent nuclei. I is having the spin of the electron, and that determine how many number of lines, but it doesn't determine the intensity. So here when we go for the B of Z is equal to 0, that is in absence of magnetic field, and when B of Z not equal to 0, when we put the magnetic field. So the applied magnetic field aligned with respect to the spin or opposite opposite to their spin. Based on that, there is having interaction would takes place. So M of S minus 1/2 and M of S plus 1/2. While in case of NMR, it is a completely complementary, opposite way. But in ESR, we get such type of peak. And there is a transition would takes place from M of S minus 1/2 to plus 1/2. And during that process, they have to absorption of the certain wavelength of radiation. And that used to be only 1 peak, 2 peak, 3 peak, based on the this equation, that is a 2Ni plus 1. So we have to see how it is work. So when we see the relative intensity of interacting nuclei, this example tells us idea about the suppose same element having number of isotopes, means Si 28, 30, 29. So in the same case, there are having different isotopes. So each isotopes having its own number of lines. So Si 28 and 30, it used to be only one transition because of its having unpaired electron on nucleus and electron interaction. Similarly for Si 29, it used to be 2 peak, and when combination of all, it used to be 3 peak. So that way one is having major peak, so this one is major peak, and these two are minor peak, but we get the 3 peak with combination of 3 isotopes. So that way we get how there is a multiple nuclei interacting, and based on its derivative, we can able to understand how many unpaired electron present in that the particular element or molecule or compounds. Intensity is one of the key aspects to understand how it works. Why intensity? Because it mainly depend on the I is equal to plus 1/2 or minus 1/2 or whatever it may be, spin quantum number. So this is the relative intensity. N is nothing but the integer. When 0, 1, 2, 3 like to be that way, its intensity is 1, 1:1, 1:1, 1, 3, 3, 1 like to be that way. So we see the example of methyl radical. It is a very common example for us to understand how it is showing the number of 4 peaks and why it show the 3 intensity. Here n is equal to 3. It used to 1:2, 3:2, 3:1. So here also we get like to be intensity with respect to this, but having 4 signals. How we get it? For methyl radical CH3, 2 into n. N is having integer, but having the 3 hydrogen atom. So therefore n is equal to 3. And spin of the hydrogen is 1/2 plus 1. We get the 4 signals, and that 4 signal we get it. So this figure tells us these are the intensity with respect to applied magnetic field. It used to be having majorly it used to the 4 signals. So similar to that way, we go for the relative intensity for I is equal to 1/2 and n is equal to 1. We get the 2 peak, 3 peak, 3 peak. N is equal to n is nothing but the integer. When 2ni plus 2n, n is equal to 1, I 1/2 plus 1. So by that way we get the 2 signals. 2ni plus n is equal to 2, I is equal to 1/2, we put it, we get 3 signals. So that way we get the signals with respect to I of the spin of the electron, and n is having integer. When relative intensity I is equal to 1, at that time their intensity should be vary with respect to n value. So that is a different one. In this case, when I is equal to 1 and n is equal to 1, 2ni plus 1, 2n, n is 1, I is 1, so 2 plus 1, so it used to be 3 peak, 2 plus 1, 3 peak. Like to be that way we get the how many peaks with respect to relative intensity. This is the simple way of calculation to understand. Then for this C6H6 free radical or benzene anion radical, during that they have to show how many peaks or signals 6 equivalent hydrogen atom. So 2n is equal to 6. I spin is having 1/2, so we get the 7 lines with having relative intensity this one, because I is having 1/2 and n is having 6. So like to be we get the 7 line. I hope so. Here n is equal to 6. So this is the last case. Where here, so we get the signals. So this is the signals where we get it. And then for the naphthalene anions, during that there are two way of proton. One is equivalent. One group is alpha, another group is a beta. So alpha group, so this portion of alpha group having equivalent 4 proton, and beta group having 4 equivalent protons. So we get n is equal to 4 in both cases, because both have cases that is 4 4, and spin is having 1/2. So we get the 25 ESR signal. So the hyperfine interaction of this molecule also, pyrazine anion, also showing two equivalent nitrogen atom. So up and down when I is equal to 1. So 2Ni plus 1 we calculate 2n, n is having 2 because 2 nitrogen atom, spin I is equal to 1, so we get the 5. Then couple with 4 equivalent of proton, proton having spin 1/2. So 1/2 2Ni plus 1, 2 into n, n is having 4 hydrogen, therefore 4, 1/2, it used to be 5. So like to be that quintet intensity we got it from this pyrazine anions. So these are the way how we get the signals for this one. Then another one, bis-salicyladimine copper. Here also we have to see the two equivalent nitrogen, the cross nitrogen are equivalent having spin 3/2 in 4 group signals. Again we get the 4 signals, 4 group signals. So they have to be split in major 4 group, while they have to further split it in 2 nitrogen and 2 equivalent hydrogen, and from that we get the 15 lines. So that way quintet with intensity, this ratio quintet of intensity we got it. So benzoquinone radical also 2Ni plus 1. So n is equal to again 4 and 4 protons. Spin is having 1/2. It used to be 5 signals for benzoquinone radical. And this one is a example where we get it CF2 where CF2H radical and another one CF2H radical. Only isotopes should be variable, 2Ni plus 1 and 2Mi plus 1. So 2 into 1, 1/2 plus 1, 2 into 2, 1/2 plus 1. So this is for 1 means this is for hydrogen, and this is for the fluorine, but both are having spin 1/2 1/2. It used to be 6 line for this molecule. For this molecule, carbon is also having isotopes with 13, not 12. And due to that reason, what happened? It shows the 3. So 2, 1 for carbon integers, spin 1/2 plus 1, 2 into 2, this is for fluorine, 1/2 plus 1, and this one 2 into 1, this is for hydrogen, 1/2 plus 1, it used to be 12 signals. So that way we get the how many signals or lines from this ASR spectroscopy. And then last points which we are actually aware about this. What are the problem, what are the possible cause, and what we have to do it. So suppose in spectrum we get many signals, many peaks. So mixture or compounds or chemicals which are having complex one, and it is a non-equivalence. So what we have to do, we go for the effective separation and use the 2D technique. Secondly, suppose few peaks are present in the spectrum, it means that it is having possible cause is inter or intramolecular exchange process. So for that purpose we have to record that this spectrum at lower temperature and using different solvent. Also, so there is also possibility due to accidental overlap of P. Therefore, we got the very few peaks. So again, a record with having different magnetic field. Suppose some peaks are very broad. So what happened? What are the possible cause? Exchange process occurring, poor sample preparation, quadrupole nucleus may be present, and paramagnetic compounds. Secondly, under that, what suggestion is given? Record spectrum at lower temperature with having different solvent. We have to use also mobile solvent and having no solid may be present in that during the sample preparation. Then strange non-binomial and a pattern observed. So at that time possible cause is a second order spectra, accidental overlap of peak. And furthermore, record on high field machine and simulation pattern by calculation. So with these information, we get how this ESR spectroscopy tools is useful for a wide range of applications. I hope so it is would be beneficial for you. Thank you so much. Thank you.